Okay, welcome everybody. It's an honor for me to introduce the next speaker. This is Simrit Sturren, known for her many contributions in robust optimization, but also in other topics of optimization. But today is about robust optimization, and the topic is robust adaptive scheduling. So please, Simrit.
Hi, thank you, Dick, and thank you for inviting me. I'm going to present today a work which is still ongoing about robust adaptive scheduling, and this is a joint work with Yitzhak Cohen from Bar-Ilan University and Krzysztof Kostek, that you all probably know, for Erasmus. And just to start, let's talk about the scheduling problem. When I talk the scheduling problem, there are many scheduling problems, so I will try to kind of focus us more and more as the presentation goes of what kind of scheduling problems we're talking about. So we consider a problem of scheduling n tasks on n machines. We have a lot of tasks. Each one may have a different duration. And here we see like 6 tasks and 2 machines. The machines, of course, can be identical and can represent, for instance, workers or computational resources that we want to that we need in order to complete the task. They can be different machines, or they can be the same kind of machine, but maybe with different processing speeds. But in this talk, we're talking about the maybe simplest form of the problem where we have identical machines. Also, we talk about the problem with each task require only one machine, so you can think about it as one unit of resource. And the task cannot be preempted or partitioned, meaning that we can't stop the task in the middle and continue the rest of it after a while. And we also can't do like half the task on one machine while simultaneously doing the other half on the other machine, for instance. And the goal we're discussing is minimizing the maximum completion time, also known as the make span of the problem, meaning the completion time of the last task that is finished. There are various others objectives that are considered in literature, and each one has its own properties, but we are focusing on the make span. The reason is this project came about from considering project management problems. And in project management, a lot of the time, what we're actually considering is when the project will end, okay? But this is a simplified version. We first look at the scheduling problem. So there is vast literature on scheduling problems. And here I state 3 books, and I'm sure there's a lot more. And the literature mainly talks about complexity, formulations, approximations, and algorithms. And scheduling appears in a vast array of application. As I said, task scheduling on servers, on the cloud, airport landing and liftoff scheduling. There was, I think, 2 sessions on that, on Informs last year, production planning and project management, and various more. So this is a problem that is still very alive and attracts a lot of interest. So in order to understand the problem better, let's first look at the deterministic setting. So in the deterministic setting, for each task, we know the exact duration. And this is also called this problem of scheduling to minimize make span on parallel machines, which are identical. Parallel machine scheduling, it's used as an acronym in the literature. And it's equivalent to, or very similar to, a problem that is the M-partition problem, in which we want to partition a set into subsets which have approximately the same size. And for the deterministic problem, if we're looking at the make span, minimizing the make span, then actually the ordering of the tasks on each machine is irrelevant. We just need to decide which tasks belongs to or will be scheduled on which machine. and we can flip the order. And despite it being the easiest maybe form of the problem, it still can be hard. And of course it has, there's a well-known mixed integer optimization formulation for this problem, and it can be solved through dynamic programming. And there are multitude of heuristic techniques, and just one of the surveys on heuristic techniques for this is Mokotov from 2001. There are many more. So what happens when we start considering uncertainty in these kind of problems? So first we need to describe what we mean by uncertainty. So uncertainty with regard to the durations of each task. And of course we can consider the uncertainty to be stochastic. So we are giving the distribution of durations of tasks, or the joint distribution, and we want to minimize the expected weight make span. There's also the robust way of looking at uncertainty. So we're giving an uncertainty set where the task durations may lie, and we want to minimize the worst case. In both these cases, we can consider static policies and adaptive policies. So we'll first talk about static policies, understand what kind of static policies there are, and then we can continue and talk about what really interests us, which is the adaptive policies. So even in the static policies, there are two kinds of static policies that are considered in literature. The first is called priority-based schedule. And in this schedule, the order in which tasks are allocated to a free machine is predetermined. So just as an example, we have a list of tasks and their durations is uncertain, but we decide that we allocate task 1 and then task 3 and then task 2 and so on. So we start by allocating, because we have two machines here, task 1 and 3, and then 3 happens to finish before task 1, and so we allocate 2. Now 2 finishes before 1, we allocate 4. Now 1 finishes before 4, allocate 5, and at the end we allocate 6. So obviously the order or which task will be on each machine depends on the realization, okay? So, but the order in which we allocate is predetermined, and that's why it's still a form of static policy. The other static policy is permutation. Hi, Ronnie? It's permutation-based static schedule. And in this static schedule, we decide ahead of time which tasks are to be scheduled on each machine and in what order. Okay? So this would not change regardless of the realization. And there are many stochastic and robust, the literature on stochastic and robust scheduling with static policies is also quite vast. There are various mixed integer optimization formulation for variants of these. There's a recent work about an approximation technique for static robust policy with budgeted uncertainty sets. And there is very little work on solution characterization that we'll get back to later on. So when we talk about adaptive policies, the story is a bit different. In adaptive policies, each time a machine becomes available, the decision is made on which task to schedule. So the scheduling decision is based on the information that is available at the time the decision is made. And at the time the decision is made, we know what tasks have already been finished and their duration. We know what tasks can be scheduled, and we know what tasks are still processing and how long they have been processing for. So our structure of information is very rich, but also very complex. And this is, I think, the main difficulty in this application that is different than what we are used to, maybe in what we usually call multi-stage robust optimization. Because here, not only the scheduling decisions, but also the decision points, the points in which we make decisions, and the information that is available at these points depends on prior decision and also depends on the realization of the uncertainty. In order to understand this better, let's think of call it traditional multi-stage problem, in which you make a decision, some uncertainty is revealed at time 1, you can make a decision based on the uncertainty revealed, then more uncertainty is revealed at time 2. Now you can make a decision based on the 2 parts of the realization that have been revealed, and so on and so on. When we talk about adaptive optimization, the story is more complicated. First of all, consider, for instance, that we decided to schedule task 1 and 3. First of all, the point in which we make a decision will be the point where the first one of them finished, and that depends on the uncertainty, on the parameter which is uncertain. So we will make the next decision at the time which is minimum between D1 and D3. Okay, so it's based, the decision point is based on our prior decision, which is that we decide to schedule 1 and 3, and on the specific realization of the uncertainty. Now, once we have a decision point, we are revealed if 1 ended before 3, the duration of task 1, as well as the fact that task 3 is longer than task 1 or is longer than the current point in time. But we could have gotten a different type of, a different set of information. We could have discovered that task 3 finished now, and the task 1 is bigger, the duration is bigger than the current time. And now we need to make a decision that is based on this specific information that is revealed. So if this explanation did not satisfy you that this is a more complex problem than traditional multi-stage optimization, let's go back to the sources. As the scripture, the robust optimization book, that there's a whole section that was with the project management problem and the complexity there of determining decisions. But it's still relevant for the scheduling problem too. And I like this quote because it captures the essence of the problem in this adaptive scheduling scheme. The attempt to fully utilize the possibility to adjust the decisions to actual values of the data results in an extremely complicated problem. Not only the decisions themselves, but the very information base of the decisions become dependent on the uncertain data and our policy. So this leads to, so basically our policies are more complicated. The information structure in which the policies depend on becomes more complicated. So we wanted to understand more about the optimal solutions of these kind of problems. And when digging in literature, we found very few papers that deal with the differences between static and adaptive solutions in this context, and that have some insight into the structure of adaptive policies. So the first one is, both of them are for the stochastic setting, not for the robust setting. The first one deals with both makespan and sum of completion time. And as you can see, it's work from the early 80s. And it deals with the conditions under which static priority policies are actually optimal. And And it's for when the task duration is distributed exponentially and all and various other monotonicity conditions on the problem itself. The additional work that we found that deals with the characterization is about when weighting should be considered as part of the optimal policy. And the only paper we found on this is a paper by Yetzen from 2003, but it deals with a different setting. It deals with the setting of sum of completion time and again, the stochastic setting. And it shows that optimal policy needs to allow for weighting. I'll answer the question, why is weighting so crucial to understand if weighting should or shouldn't be allowed, maybe a bit later. So what do we deal in our research? Finally, we are back here. So I focused on the 2 parallel machines. Some of the results can be extended to M parallel machines. Some of them cannot because of the complexity, or we did not include the complexity. And we talk about the robust setting. We try to characterize optimal solution in static and adaptive settings. And specifically, we want to understand, would the adaptive and static policies give different here and now decisions? We know that for a lot of multi-stage problems, although the policies that are given by static and adaptive decisions may be very different, if you actually look only at the here and now decisions, they may be the same. And so if you apply a method, like a method for solving multi-stage programming via folding or rolling horizon, the fact you might not need to solve the adaptive problem. It might be enough to solve the static problem with a smaller problem size. So we wanted to know if we can identify cases in which they're equal or not equal. And the second question, when is a policy with weighting better than one without? And weighting is interesting because when you allow for weighting in scheduling problems, the problem, which is hard enough as it is, becomes even harder because you don't know how much weighting you need to allow for. So you have this continuous variable that you're not sure of the duration that you need to account for, how many times should you allow for weighting, is it after every task, and so on. And so to allow us to better approximate or solve the problem for this problem and more challenging problems, we want to better understand the characteristics of these solutions. So we start with an example. So consider very simple examples. We have 3 tasks to be scheduled on 2 machines. The durations of the tasks are given by a linear duration of task 1, task 2, and task 3 are given by linear functions of uncertainty, where the uncertainty is kind of a non-negative budgeted uncertainty set. Okay, so each uncertainty Zi is between 0 and 1, and the sum is smaller or equal to 2.5. And let's first look at the static schedule. Okay, so we have a static schedule. I'm skipping a bunch of steps which needs to be proven, but in the optimal static schedule, 2 and 1 should be scheduled on one machine. When I'm talking about the static schedule, I'm talking about a static permutation schedule, and 3 on the other machine. So this is the optimal static schedule, and under this static schedule, the worst case duration is 1.9525 with the worst case realization of 1, 1, and 0.5. However, there's something a bit odd about how we compute this worst case. Because we considered a static problem and a static schedule, we did something that we would not do in practice. We see that in the worst case, task 3 finishes before task 2, and yet we still schedule task 1 after task 2 and not after task 3. So if we said, okay, so let's assume that we only applied the here and now decisions for this solution. So we schedule task 2 and task 3 in parallel. And then after the first one finishes, we will schedule task 1. So are the here and now decisions, what will happen then? So first of all, of course, we reduce the make span of the problem, okay? And the realization, the worst case realization changes significantly. And as you can see, in the worst case, task 2 and task 3 have the same length. But the question is, okay, so this is how we can evaluate a given here and now decision for this 3-task problem to give the true adaptive make span for the here and now decision that we got from the static solution. But now the question is this also the optimal adaptive solution? Would these 2 tasks be the ones that would be scheduled in the beginning? And the answer is no. Actually, if we solve the adaptive problem to begin with, we will schedule task 1 and task 2, reducing the make span by an additional 0.08 approximately and changing the worst case. So the first stage decisions, as we can see here, are different. But it's not only different, actually, let me go back. There are 2, if I look at the static solution, because I'm looking at a static permutation schedule, it doesn't matter if I schedule 2 and then 1 or 1 and then 2 on the first machine. They both will give me the same objective value, the static solution. But both will give me a suboptimal make span if I apply the first stage decisions. So it will never be optimal to have a task 2 and 3 in parallel or task 1 and 3 in parallel to begin with. It's only optimal to have task 1 and 2 in parallel. Okay? So here, of course, the difference between the numbers is not gigantic, but we can conclude from this very simple example that the optimal static permutation schedule and the optimal adaptive policy to the robust scheduling problem may lead to very different here and now decisions. And so the implications of this is that ignoring adaptivity may lead to suboptimal decisions. And it's not only that the suboptimal decisions because the policy is suboptimal, but even if we only apply the here and now decisions that are obtained from the static policy and adapt them afterwards, we may still obtain something which is suboptimal. And more so, even if we do a folding horizon approach, because we still apply suboptimal here and now decisions, we may get something suboptimal. So this answers the questions about whether first stage solution or here and now solutions for the robust scheduling problems are different between when considering static versus adaptive. The next question we wanted to answer is, do we need to consider weighting when looking at policies? So do we have to consider policies which include forced weighting as part of the policy or not? So we start with the static case. And for the static case or static permutation schedule, we can say that we can ignore the option of weighting because there will be always an optimal policy in which there isn't any weighting. And the solution is very simple, and I show it graphically. So let's assume we have some optimal permutation schedule, and the optimal permutation schedule has some weighting somewhere after task I. So here in the example, we have an optimal schedule, and this is the worst case realization, let's say, where we have a weighting W between task 3 and task 2. Okay, regardless of the realization. Now, for any realization, limiting this waiting time will not increase the make span. Okay? This is true not only for the worst case realization, but for any realization. And since this is true for any realization, eliminating the weighting would not affect the worst case. So we can always find a worst case, always find an optimal static policy which does not include weighting. So we solved this problem we solved these questions for the static case. But what about the adaptive case? In the adaptive case, the situation is a bit more complex because weighting may provide information about the duration of the task that may enable us to make better decisions in the future to reduce the make span. So if this information can be translated to decisions that shorten the make span, then of course we need to consider weighting. And first of all, we showed that in some cases this cannot happen. For instance, if we have a box uncertainty set, meaning each task has a segment for its durations and it's independent regardless of the realization, then we can always show that weighting is not needed. We can always find an optimal policy without weighting. And actually in this case, the adaptive and the static policies will be the same. What I said that's true. The adaptive and the static policies would not be the same, but their worst case duration. So we still need to answer in the general case, is there always an optimal adaptive policy without weighting? And again, let's return to an example to understand this problem better. This is a very simple. It's a simple example, but you will see that even for an example with 2 machines and 4 tasks, the amount of things we will need to consider is the problem becomes very complicated very fast. So consider the case where we have 4 tasks and we have a scenario uncertainty set. So the uncertainty set contains 5 different scenarios for the task or the duration of each tasks. And we now try to analyze this problem to try to find the optimal adaptive schedule without weighting and see if we can find a better one with weighting. So let's assume first that the weighting is not allowed. And I need you to believe me that the optimal task to schedule are task 1 and task 4. In order to verify it, you need to go over all the possible tasks to schedule at the beginning. But if you do that, you will also discover it's task 1 and task 4. And we now only look at the scenarios for which one finishes at time point 25. In this case, it's optimal to schedule task 2. And then we have 2 different scenarios that might happen for the duration of task 2. The first one, task 2, finishes before task 4. And so we will schedule task 3 after task 2. And in the second one, task 4 finishes before task 2. And we'll schedule task 3 after task 4. So the first scenario will give us a make span of 5.5, the second 7, and altogether, the worst of both of them is a make span of 6. Now, for the scenario when one finishes at time 2.5, we know that there's only one such scenario, and task 4 will finish at time 4, so after task 1. We can now consider 2 possible options, either schedule 2 after task 1 or 3 after task 1. And for both these options, it's pretty easy to compute the worst case from the 2 schedules, from the 2 possible scenarios that we have. And the make span for both of these will be 7.5. Finally, we have one remaining scenario in which task 4 finishes before task 1, and we know all the durations of the tasks in this scenario, and so the make span is 7. So the worst case make span over all these different possibilities for when task 1 finishes versus when task 4 finishes is given by 7.5. So I think this example also illustrates what kind of different information we may get in different points in time and how we can adapt our decisions accordingly. So this is the case where we did not allow for weighting. Now let's look at the case that we allow for weighting. And let's say we allow for weighting of at least 0.25, of exactly 0.25 units. So remember, in the scenarios of task 1, there are 2 scenarios in which task 1 finishes in exactly 0.25. Okay, so at 0.25, we will know if we're in one of these scenarios or in one of the other 3 scenarios. So one option is, that's what we did, and task 1 finished at 0.25. We now have 2 free machines. And again, you can look at all the combination of scheduling 2 tasks to those free machines, and optimal scheduling is 2 and 4. And we have 2 different scenarios for this schedule. And in one of the scenarios, the worst case max span will be 5.75, and in the other, it will be 7.25. Now, in the other case, one doesn't finish at 0.25, so it still continues. And then we need to decide what task we schedule in parallel to task 1. And again, we need to look at all the options and bid, and the optimal task to allocate is task 3. And now again, we have task 3 will, in the case that it finishes after task 1, we will schedule task 4 on first machine, and task 2 after task 3. And again, we have 2 scenarios here. And in both cases, we have a make span of 6.5 and 6.7. Okay. Again, this is not the last schedule we need to consider. We need to consider the schedule where task 3 actually finishes before task 1. There is only one such scenario, and this is the optimal schedule for that scenario. And the make span here would be 7.5. So in total, we have the worst case with make span with weighting is 7.25, which is lower, strictly lower than 7.5, the worst case without weighting. So the information we gained by partitioning these scenarios to 2, the one that have 0.25 versus the one that are larger than 0.25, enabled us to get a 0.25 reduction in the make span. And we try to understand if this is so this, first of all, gave us this conclusion that there are cases where optimal adaptive schedule must include weighting. So if we disregard policies with weighting, we might throw away the optimal adaptive schedule. But as you can see, that this was a scenario uncertainty set. And although these uncertainty sets are used in practice, in a lot of applications, we want to use convex uncertainty sets, budgeted uncertainty sets, L1 type uncertainty sets that kind of capture maybe a bit of the correlation between the tasks. And the question that we ask is, okay, so if we only consider such convex uncertainty sets, is weighting still needed in general? And we are working on this problem currently, and our current conjecture, and it changed a few times, but this is what we believe now is true, and we're trying to prove it, that for convex uncertainty sets, weighting will not be optimal. And it's something about the information gain that is reduced when you have something that is continuous and convex. The information you get about the other tasks, about how they change, is not enough, basically, for weighting to be beneficial, because you need the information you gain to somehow balance the time you lose by weighting. And so we're trying various ways now to prove it in a lot of simulations that we did. We have not found one case in which weighting was in fact beneficial, that it got a better result than a policy without. And so, in summary, what we got so far from this project is we can't ignore adaptivity when making decisions. And although the problem of adaptive scheduling is hard, it might be worthwhile trying to tackle it in order to see if we can, the here and now decisions that we obtain give us much better solutions than in this case. We'll gain insight about the role of weighting in adaptive policies. And as I said, weighting is very important. Know if we need or shouldn't consider weighting, because when we try to solve this problem via dynamic programming, or when we try to build approximation technique, considering weighting makes the formulation, the heuristic, much more complex. So, of course, the dynamic programming is still, even if we don't consider weighting, it's not an easy thing to solve, but if we need to consider weighting, it becomes much more complicated. You need to, for instance, discretize the amount of weighting you have and try to find what is the optimal weighting at each point in time, which is an additional difficulty to just scheduling the tasks themselves. That's all. You were all very quiet and did not ask questions during, so I welcome any questions you have now.
Thank you very much, Shimrit. So are there any questions? You can directly use your microphone. So I have a question, Shimrit. So in the beginning, you described, in fact, two approaches. One is, let us say, the robust approach, and then also with a distribution for the processing times. But there is also another way to look at distributional robust stuff.
Sure. Yeah.
And for example, if you assume that they are independent, so maybe you can then assume, and also what Christoph did and Ronnie on the mean MED stuff. Is that an easier approach or a more difficult approach, you think?
I think in the adaptive case, it's equivalently hard, because you still need to kind of consider all the, you know what, I take it back. It might be easier because the linearity of the expectation. However, because you still need to make adaptive decisions, it still has a hardness to it, although in some cases, I think you might be able to extend the works from the 80s about the stochastic setting to maybe certain kinds of distribution robust settings for certain kinds of ambiguity set. But we didn't go into that because we are interested in the robust case. That's where we started from, so we didn't investigate the distribution in robust setting.
And if you consider a static policy and then evaluating, and let us say the value of it for a certain
static, again, even evaluating, when you said evaluating a static policy, so that's a question. Do you want to still evaluate it in an adaptive way? Because the evaluation problem is hard here.
I see. Yeah.
because the only thing you actually implement are the here and now decisions. So actually the evaluation problem of even understanding for a certain here and now decision, what is the actual worst case max span or worst case or expected max span will be difficult.
משהו קרה לי פה.
היי רוני, אנחנו שומעים אותך?
אתם שומעים אותי?
Yeah.
I think maybe a better model for the problem with different scenarios of the duration is you know the scenarios, but probably you don't know the probability of the scenario occurring.
Mm-hmm.
Uncertainty could be the probability of the PI of scenario I occurring.
Yeah.
And then the objective function should be to minimize the expected make span. It might even be an easier problem.
Yeah, that could be. We didn't look at that setting, but that might be very interesting to look at and see if we can say something more about that setting. Definitely.
Okay, other questions? So no more questions.
I could ask a question, Dick.
Erik, yeah, please.
Hi, Shimrit. Thanks for the talk. Maybe I didn't listen carefully, but is there a result for the stochastic version of your problem regarding whether weighting is needed?
No, not for make span. Not for make span. There are some results about the sum of completion time, but not for the make span version.
For the expected make span in that context.
Yes, yes.
Okay.
And the results are like the results that do exist are you need to account for weighting for the sum of completion time. But I think that's more intuitive when you talk about sum of completion time, because then it really matters when each task completes. So it makes it, I think it's more intuitive at least to expect that weighting might contribute there. Even if it doesn't contribute to the final completion time, you can somehow play with the task. But for us, at least with the make span, it was not as clear.
Okay, thank you.
More questions?
Yeah, I would also have a question.
Yeah, Dirk?
Yes.
Yeah, thank you very much for the talk. So I was just wondering, do you have some intuition on how we might be able to find the adaptive first stage decisions for general problem?
So that's something we're planning to do next. We have some MIO formulations. We have some kind of dynamic. Again, if you don't account for weighting, you can write a dynamic programming scheme. You can write an MIO formulation for the problem, but it involves a lot of kind of partitioning of the problem in a way which is, again, a bit different than what we were used to, because the information may be slightly different and you can make different decisions. I think the dynamic programming approach, if no weighting is actually optimal, would be the easiest. Of course, it has its disadvantages with scale. And we're also trying to think of heuristics that we can use in order to get maybe not the optimal adaptive policy, but a good one that is based on kind of rules that are used in practice. Or kind of a partitioning, which is, again, might not be the optimal partitioning, but still get us the gains that we get from the adaptive setting. This was kind of a preliminary work because we wanted to understand what we need to look for when we're looking for adaptive policies, and what kind of policies we can eliminate from the get-go. And things surprised us here, because at first we thought weighting, because of the way, because you do spend time, you do waste time when you wait. It took us a while to even get to a place where we found a scenario where we saw the benefits for waiting, and we because we wanted to understand it, because we understood that if we need to account for weighting, things become much more complicated. But yeah, it's one of the things that we're working on and planning to work on for a while, is how to solve this problem once we understand more about the optimum solution.
Thank you very much, Simrit. Looking at the time, I think it's already 3:45. So many thanks for your interesting talk.
Thank you for your comments and for your attendance.
Yeah, so next week we have, of course, another webinar, and I'm also asking for potential speakers for after the holiday. So if you would like to give a presentation in this robust optimization webinar, please contact me. And especially I would like to stimulate PhD students for this, because, you know, for them it's now not possible to present during conferences. So I stimulate them really to contact me for a talk after the holiday. Okay, thank you very much. See you next week.
Thank you.
Thank you, Dick.
Thank you. Bye-bye.